Hey, let's take a look at the atom, some basic facts about it. Let's start with the simplest possible atom, a hydrogen atom, a one-electron system. We've got a electron that is in the nearby to a nucleus, and that electron is only about 10 to the minus 18th meters in diameter. That is pretty small. The nucleus is about 1,000 times larger, 10 to the minus 15th meters. That's very small also. And overall, the radius of the atom in its ground state, meaning that electron has not gotten excited and moved out any further, would be about 1/100th of a nanometer. That's 10 to the minus 9th meters. So atoms might be in the realm of 100th of a nanometer for the very small ones, up to a nanometer or larger for the really big ones. So atoms are in the nanometer scale. The composition of them is protons, neutrons, and electrons, where there are protons and neutrons in that nucleus. And the average mass of hydrogen for that system right there would be about 10 to the minus 24th grams. That is a exceedingly low mass. Or you could just look up the number on a periodic table where its average atomic mass is 1.008 AMUs. Atomic mass units, which is kind of a unitless thing. In case you're curious, where'd that come from? Well, if you had 6 times 10 to the 23rd of these atoms, that would be its mass in grams. The average mass of carbon is about 10 times larger, 12.011 AMUs. Why? Well, you've got more nuclei, protons and neutrons, and you've got more electrons, although these don't contribute much, do they? In fact, you've got 6 protons and 6 neutrons. Notice how this number is very close to 12. The mass and charge of the electron is very interesting. That thing is 10 to the minus 28th grams. Now that is an exceedingly small number. And it's, less than 1,000th of an AMU. It's generally just rounded off to 0. And it has a negative charge, which simply means it's attracted to something with a positive charge. Now that number is very interesting because that's the point at which matter becomes so minuscule that it's starting to have characteristics similar to light as well as matter. They call that the particle wave duality. The mass and charge of a proton is about 1,000 times larger, even a little more than that, and the mass and charge of an electron is very similar. Notice the slight difference there, whatever. Did I say electron? I meant neutron. And so these come in at about 1 AMU each. Let's take a look at some properties of electrons and how they move around in the atom. This was studied first using hydrogen, smart move, very simple system, and it was looked at from the point of view of light. Imagine sunlight. You see all sorts of visible wavelengths from 400 to 700 nanometers. But if you look at an ionized gas form of hydrogen, that's hydrogen plasma, you see 4 very sharp visible lines. That was known, 150 years ago, and it was also determined not long thereafter that it follows a mathematical pattern. There's clearly some useful data here. You've got sharp exact numbers that seem to be coalescing, getting closer together as the wavelength gets shorter. The pattern was eventually determined to follow this sort of an equation. That wavelength in nanometers can always be calculated given 2 integers. And that's exact whole numbers. Isn't that cute? So it's 1 over 0.01097. This became known as the Redbird Constant. This is the Balmer formula. And you need 2 whole numbers. Bohr put it all together by realizing these could be thought of as shells around the electron. Outer would be the larger number, inner would be the smaller number, and that's where this light is coming from, is electrons going from the outer to the inner shells. We call this electron emission, or sometimes atomic emission, and that's what will happen. As an interesting detail, you'll see visible light if it ends up in the second shell, because mathematically that always ends up being somewhere between 400 and 700 nanometers. Try it for 3 to 2. 3 is your outer shell, 2 is your inner shell. If you plug in a 3 there and a 2 there, a quarter minus a ninth, you'll end up with 656 nanometers. That has real meaning. So it's good to know the math, but it's also good to know what's physically believed to be occurring. That little line right there, this red wavelength of light, this photon of light, is being caused when an electron in a hydrogen atom goes from the third shell to the second shell. So that's a different model of the atom than other people had thought of before. We have electrons residing in shells, and it is atomic emission like this when you travel from an outer shell to an inner shell that creates light. So an electron could be going from the first shell to the third light. What color light would it produce? That's a trick question. None at all. It's absorbing, not emitting. But if you go down from, say, the third to the second, you'll get a photon of red light. If you go to the fourth to the second, you'll get a photon of, well, let's call it teal light. The fifth to the second, we'll consider that one. Maybe that's teal. Maybe that's green. Maybe that's teal. But you'll get another photon of light. And even going out from the sixth to the second can be calculated as well. So this is the Bohr model of the atom. It works nice for a one-electron system. If you get a little more complicated, going up simply to helium or looking at it in more detail, the system becomes immensely more complex for a couple reasons. One, you've got two electrons, and there could be some interaction there to consider. And two, we're treating electrons here as though they're like forms of light, and they have both light and matter components to them. And so we'll need more complex solutions to this. Enter the Schrödinger formula. And that's another topic. This is an introduction to the atom.